Welcome student to the next lecture of halogen derivative, and this is lecture number 12, and today we'll be studying about energy profile diagram for SN2 mechanism. Student, we have seen what is SN2 mechanism in great depth in the last two lectures. One part is left of SN2 mechanism, and that is nothing but an energy profile diagram. Okay, if you remember the reaction, what we have done was CH3Br when it was treated with what? With KOH, or I can take NaOH. Product was CH3OH plus KBr. If you remember, that was a reaction, and this is a reactant, or I can say this is a subtract. This is what? Substrate, right? This is what? Substrate. This is a nucleophile. This is what the product is formed, right? Obviously, when I say energy profile diagram, that means this diagrams give you information about the energy of a reactant as well as the product. Okay, let's start with that, and whatever required I'll be explaining you. In this we draw a graph. What is graph? Graph is of, obviously we know there are two coordinates in graph, right? Here there's a potential energy, and here there's a reaction coordination. This is called reaction coordination. Means how the reaction proceeds. Okay, see, when we start with the reaction, we have reactant, right? And reactant have some energy. Okay, suppose the energy of that reactant, I say at the start of the reaction, this is the start of the reaction, right? So at the start of the reaction, this is the energy of reactant. Okay, now as the reaction proceeds further, okay, energy of this reactant increases. Okay, so the graph will go like this because the energy is increasing. Okay, it will go to a certain level. After that, it was observed that it comes back, and when the product is formed, suppose this is the energy of a product, right? This one is reactant, I write as R. This one is product, I write as P. This is the energy of a reactant, and this is the energy of a product. That means what we can understand from this, product has less energy than that of reactant. Okay, so if product has less energy than that of reactant, that means product is more stable. We have studied that the energy is less, stability is more. So here the product energy is less than that of reactant. That means product is more stable. Now the question is, why that reactant does not directly convert into product, and the graph comes like this? Why there's an increase in the energy here? And what is this point? This is called student transition state. I write as in short TS. This is what? Transition state. Transition state is a that position in a chemical reaction where the energy is highest. We can see from the graph also. Energy is increasing, it reaches to the maximum level, right? After that, it starts decreasing and the product is formed. Okay, and this difference in the energy of a reactant and transition state, this difference we called as delta E. This is what we call as delta E, and this is nothing but energy of activation. What is energy of activation? This is minimum amount of energy which is required so that the reactant get converted into product. Means until and unless the energy does not reaches here, the reactant will never turn into the product. So this is what we call delta E, right? And what is this delta E? This delta is called energy of activation. I can write here in small ACT. That is energy of activation. Okay, student. Right. So here is reactant. Here is a transition state. Okay. And the difference of the energy between transition state and the reactant is called energy of activation. Right. And one more. If you see this energy, product energy is less than that of reactant. So this difference in the energy of a product and the reactant is called delta H. What is that? Delta H, heat of reaction, yeah, change in enthalpy. What is delta H? Delta H is nothing but heat of reaction or change in the enthalpy. I can say it is change in enthalpy. And can you tell me delta H in this case is positive or negative? Delta H in this case will be positive or negative. Right here, see the reactant energy is less. If I have to find delta H, it will be H2 minus H1. This is final enthalpy, this is initial enthalpy, and final enthalpy is less than that of initial enthalpy. Let's assume this final enthalpy is 10 and this is 20, right? So answer is coming to what? Minus 10. Okay, student, just to this is not a proper value, just to make you understand, I wrote. That means whenever the product has lesser energy, delta H will be negative, and whenever the delta H is negative, process is what? Exothermic. So this process is exothermic. Right? It can also possible, not for this reaction, but maybe for another reaction, the energy of a product is greater than that of reactant. So when the energy is greater, okay, then in that case delta H value will be positive and the process will be endothermic, right? But if the process is endothermic, that means product is less stable than that of reactant, but here the product is more stable than that of reactant. Student, clear? Okay, so this was all about SN2 mechanism and SN2 reaction. Okay, this was the small part which was left for SN2 mechanism, and we completed this. Okay, now we'll be starting with the next, that is SN1 mechanism. I continue here only. SN1. Okay, or in our textbook it is also mentioned like this SN, and here they have written 1. Student, it makes no difference however you write, you have to understand the meaning of this. What is S? S is a substitution, N is nucleophilic, and 1 is unimolecular. That means during the process only one molecule get involved in the reaction. Okay, now student, before we go in the depth of this reaction, let's recall one thing which you have studied in 11th. What is that? That is called carbocation. You remember what is carbocation? Okay, carbocation means that species which have positive charge. Okay, we have to talk about the stability of carbocation, because in this one of the transition state there's a formation of carbocation, and in one step there's a formation of carbocation. So we have to understand the carbocation, we have to also understand the stability of carbocation. Okay, now suppose I have CH3 plus, I have CH3 CH2 plus, I have CH3 CH3 plus, and one more CH3 plus. Okay, this is methyl carbocation, this is ethyl carbocation, this is isopropyl carbocation, this is tertiary butyl carbocation, right? All are carbocations since they carry positive charge. Carbon containing positive charge. Positive is cation. Carbon containing compound is called as carbocation. Now, what we have to understand, which is more stable and why. Okay. In this student, if we talk about methyl group, okay, this is the least stable. In comparison to this one is more stable. What is more stable? The reason is it is attached to a methyl group, and methyl group, by the virtue of inductive effect, will try to push its electrons in the empty orbital of this carbon. Student, remember I told you whenever there's positive charge, that means there's an empty orbital. That means it has a place to carry take that electron, right? And here we understand already this carbon is a devoid of electron. Already this carbon has less electron. It is in need of electron. So what is going to do? It is going to accept that electron. And who is going to provide that electron? This methyl group is going to provide that electron. That means it has one friend who is going to provide him the electron. Okay, this fellow does not have any friend. Nobody is going to help him, right? So coming to the next one, here we can see that the two methyl group, right? Alkyl group has tendency to show positive inductive effect, so they both will going to give the electron, right? Not 100% electron, but few amount of electron, because if they will give up 100%, they themselves will become devoid of electron, right? So they're not going to give that much, but obviously they're going to help him, this carbon. So when they help, obviously the stability will increase, right? So here there's a one methyl group who is helping. Here we have two methyl group who is helping, and here we have three methyl group who is helping this carbon, right? So that there's a decrement in the charge, that is positive charge. So this is the most stable, right? So if I call this A, I call this B, I call this C, and I call this D, then I can say that A is least stable, then comes B, then comes C, and out of 4, D is more stable, right? Understood? Now, why we are studying carbocation will be seen when we start with the mechanism. Okay? Okay. So, now student, let's start with the mechanism for SN1. Okay. SN1 mechanism. Now, first I write the reaction. Okay. Suppose the reaction is this: CH3, CH3, CH3. I take here Br. I treat this with NaOH. Aqueous. Understand, student? This is aqueous. Okay. Now what will happen? It's again a nucleophilic substitution reaction. So OH will come in, Br will move out, and the product form will be this. Here it comes ONH. And what will be left in NaBr? This Na is going to combine with Br. So we'll get NaBr. Right? Now, if you remember, we'll see what is the mechanism of this process. But before that, let's talk about its kinetics of this reaction. Kinetics of reaction. Now, kinetics means we have also discussed that in SN2 mechanism, right? If you remember. Okay, so here the rate of reaction, student, will be directly proportional to the see, we have two reactant, right? Okay, one is tertiary butyl bromide, other is NaOH. But the rate of reaction only depends, understand student, it only depends on CH3 3CBr. It depends only on the concentration of tertiary butyl bromide. It does not depend upon the concentration of NaOH. And that's the reason it is unimolecular. That's why we say 1, S and 1. S means substitution, N means nucleophile, and 1 is unimolecular. Since this rate of reaction only depends upon one molecule, so that's why it is called as unimolecular reaction. Okay, now suppose I write like this. This is just way of writing, nothing to understand much. Right, if I put equal to sign, I have to write some constant. I'll write that constant is K CH3 3CBr. This K is called rate constant. This K is called, student, rate constant. Okay, now obviously we are going to understand the mechanism of this. Okay, let's see. This is CH3 CH3 and here Br. Right, now student, when it reacts with NaOH, right, actually NaOH when put into water will become Na plus and OH minus. The life of Na plus is in peace. It is not going to do anything because after losing one electron, it has acquired its octet, so it has become stable, so he don't want to work, so he is not going to attack, so he is not going to do anything. He is just going to be present in the reaction. But the life of OH minus is not as favorable as Na plus, so he is going to do something. But very important, student, this is where the most important part arises. Before OH attacks, what happened? This Br actually comes out, and in the first step, they do not take participation. They don't take any part. So what happened in the first step? In this first step, there's a dissociation of C and Br. Right, these bonds break, and what is formed? See, what is the hybridization of here, student? Hybridization is sp3. When I say it is sp3 carbon is sp3 hybridized, what does it mean? It means that this geometry is tetrahedral, and that's the reason I've drawn it like this. So this is tetrahedral. Sorry, tetrahedral. But what happened in the presence of OH? Sorry, in the presence of water, because we have aqueous, if you remember. See here, we have taken aqueous, right? So since we have taken aqueous, that means this NaOH is present in a large amount of water, and this water, what that water is going to do, student? That water is going to dissociate this, because this is not going to dissociate by itself, right? Water molecule will come, and this water molecule is going to dissociate this, right? How it is going to dissociate that? I show you a different color. Okay, see, carbon and bromine. Carbon is partially positive, and this Br will take the electron and become partially negative, right? Okay, when water comes, water is what? OH, H, and in this also oxygen is partially negative and hydrogen is partially positive, correct, student? So this is partially negative and this is partially positive. Same way here also it will be like this only, OH, H, right? Same way here also, OH, H. That means water will be surrounding this throughout. Okay, now what will happen? Br is negative, this H is partially positive, and there will be a force of attraction between them. That means this H is going to pull this Br to itself. Here carbon is partially positive, and in water oxygen is partially negative. So this water molecule is going to attract this carbon. means in water molecule oxygen is going to attract this, right? Here this bromine is going to attract it. During the process, see, we understand whenever there's a formation of bond, right, energy is see, to break a bond I have to supply energy. So here I have to supply energy, but from where I'm going to get energy? I'm not going to heat that. I'm going to get this energy when bromine and hydrogen forms a bond, or when oxygen and carbon form a bond. When they will form a bond, energy will be released. That energy will be utilized in breaking the bond between carbon and bromine or halogen. So this bond is going to break, student, right? So when this bond breaks, what happens? There is a formation of tertiary butyl carbocation. And what is the hybridization? 1 2 3 bond. 3 bond means it is going to sp2. Where is sp2? It is going to be what? Planar. This is tertiary butyl carbocation, right, student? This is what? Tertiary butyl carbocation. And this is the first step. This is step number 1. In first step, what happened? Right, in first step, the bonds breaks and there's a formation of carbocation. Clear? Okay. Now, what happened to the step number 2? And one thing more, student, when this step happens, this is slow step. This one is slow step. Okay, in next step, step number 2, what happened? In this step, we have CH3, CH3 and CH3. This is now planar, student, right? When I say planar, understand like this. It will be in a one plane like this, right? Since it is one plane, the attack can take place from the top as well as from the bottom. So that can be attacked from any of the direction, from the top as well as from the bottom. Okay, so now after the formation of carbocation, once the carbocation is formed, this OH minus is going to attack, right, and the product will be formed. Okay, but now the question comes, where attack will take place from which side? I mean, from top or from the bottom? 50% will be from the top, 50% from the bottom. That means there will be 50% retention and 50% inversion. Got that, student? There will be 50% retention and 50% inversion. If you remember, in SN2 mechanism, all was inversion, 100% inversion product was formed. Here the inversion product is 50% and retention product is 50%, because suppose that OH moves from top, right? So whenever the Br moves away from the top, so when OH comes at the top, that is what? It is retention, right? But if OH comes from the bottom, then it is inversion. Okay, and now the product will be formed. Okay, so the product I can write like this: CH3, 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 OH. Right. Now, student, one of the most important question, this is the reaction, this is what the step, and this is the fast step. Since it is a fast step, so the kinetics, that is rate of reaction, does not depend upon the concentration of OH. Right. In slow step, there is only one reactant. Okay, we have only one reactant. So the rate of reaction depends upon only this. Now the question comes, why this reaction does not take place like the first case, that is SN2. Why this is two-step reaction? Why does not it take place in the one step the same way as it was done in SN2? That's the question. Okay, let's try to figure out what is the reason, student. Okay, now if you see, I have C, one more C here, one more C, one more C, and suppose I take Br. And now if you think like this, there's an anti-bonding orbital. Remember we have discussed that anti-bonding orbital. Okay, suppose there's an anti-bonding orbital present over here, right? And this OH minus tries to come close to it and it tries to pull its electron in the anti-bonding orbital. Why this does not happen? The question is this: why this does not happen? We have to give some solid proof for that, solid reasons for that. Obviously, let's understand. See, if you remember, there we have HHH, right? The structure was tetrahedral. Here, this carbon is actually a methyl, right? So if it is methyl, it will have hydrogen like this. This will also have hydrogen. Okay, and here also there's a presence of hydrogen. That means there's a hell amount of crowding over here, student. Because there's a huge amount of crowding, OH minus can't come closer to this orbital of carbon. Since can't come closer, it is not able to put its electron into anti-bonding orbital of this. Since it cannot give its anti-bonding, it's not possible to put this electron in the anti-bonding orbital of this. So since it is not possible, this process is not going to take place. And that's the reason what happened, this Brs moves out, right? There's a breaking in take place in the presence of solvent. When this breaks, there's a formation of carbocation, and once the carbocation is formed, OH, who is already formed, he's ready waiting for that carbocation to come. As it arrives, OH attacks, product is formed. Right, student? Okay, so this is what SN2 mechanism. Okay, now if I talk about the stereochemistry of this is SN1. If I talk about the stereochemistry of SN1, when I say stereochemistry, what does it mean? Let's understand. See, carbon, I want, if I have to discuss about the stereochemistry, I should have asymmetric carbon. What is asymmetric carbon, student? If all the 4 group attached to the carbon is not same. Suppose I take here C2H5, I take here CH3, I take here one phenyl group, right? Okay, and then I have Br. Okay, so this is asymmetric carbon, right? When there's a presence of asymmetric carbon, okay, and once this Br comes out, right, I told you there will be 50% retention and 50% inversion. So let's draw in some diagrammatic way so that we understand here. Suppose this carbon, right, C2H5, same what is present. Here comes OH. So this is what? This is called retention. This is called retention, student. Okay, but if we take like this, here comes OH and this C become like this, right? So this is inversion. This is what? Inversion. In this case, 50% going to come from up, 50% going to be, because when the carbocation is formed, right, it is planar. So here there's a retention 50%, retention 50% inversion. And when I take this mixture, right, understand, student, when I take both in an equal quantity, in equal amount, and then I pass what? I pass plane polarized light. Then what will happen to the plane of plane polarized light? Tell me. Think and tell me. Suppose I take this mixture, equal amount, and I pass plane polarized light through it. So what will happen to the plane of plane polarized light when it comes out? Right, it will show dextro, it will show levo, what? Actually, student, it will come out in the same way. It is neither going to rotate to the right to the left, because 50% retention inversion, that means the product 50% will move in the clockwise direction and the other 50% will move in the anti-clockwise direction. As a result, this is neither going to rotate to the right nor to the left. And such a mixture which does not rotate the plane of plane polarized light is called which mixture, student? That is called racemic mixture. Remember, this is called racemic mixture. Okay, so we have studied what is SN1 mechanism, student. Okay, in the next lecture we'll obviously we'll see the energy profile diagram for SN1, and we'll also see the comparison between SN2 and SN1 mechanism. Okay, for today we stop. Thanks for watching.